Hello, welcome to this live stream. In this completely unscripted guide, we are going to talk about memory management in the C language. Let's jump right into it. Now, there are many functions that we are going to get from the standard library, which is in standardlib.h, and those include malloc, calloc, realloc, realloc array, and free. The main function you are going to be using is called malloc, which basically stands for memory alloc. And the signature of this function, so it returns a void pointer, basically. You are going to give it the size of the memory block that you want to allocate. And this memory is going to be allocated on the heap. It is you who is going to be controlling where this memory is pointing, and it's your responsibility to free it. So if I put, let's say, size of int glibc, which is the C implementation on Linux where I am using, I'm literally instructing it that, you know what, the memory manager, please give me 4 bytes, which is the size of the integer on this platform that I'm on. Now, a good thing is it's always good to use size of, because depending on where you compile your code from, it's going to give you the right size. For example, an integer may be 32 bits, but on another platform, it may be completely different. Yeah. So you say, give me enough memory where I can store an integer. So basically, this is how malloc is used. You just give it the size of the memory block you want. And if the memory exists, it's going to give you a valid pointer, which points to the memory that has been allocated. And if it fails, it's going to return a null pointer and set the error no. Error no is basically a number which kind of demonstrates, which shows you what kind of error occurred. And you can include it by including error no.h. Yeah, so basically how you use it is like you want to allocate an integer. Instead of saying, instead of using void pointer, you can cast directly to the type that you are interested in. So here I'm allocating an integer pointer. I'm allocating memory for a single integer on the heap. And if this fails, so you check like if not pointer, return 1. If you want the exact message that has been returned without printing it directly, you can print. For example, you can say printf malloc failed, and then you want the message as a string, you want to print it out, you can use str error, and then you pass in your error. And str error, you can import this from string.h. So this one will print the actual reason, as basically it will give you a string which represents the error no, and now you can pipe it into your printf and print it out. Let me demonstrate with an example. Let's say you want to create a simple string type, because in C there is no string type. So how would you implement that? You are going to declare a struct of the type string. So this is string. You give it the size, because we want to know how many bytes does it contain. So we are going to call this size. Then we are going to give it the capacity, how much memory actually is allocated for this string. And then you can give it the data. Like this is the actual memory in bytes that is stored on the heap for that string. So there are actually many strategies of how you implement this string. This is the first one, where you store the size, the capacity of the string, and then the data. And then this data is what we are going to dynamically allocate with malloc, and we store it on the heap. It means that the first example, let me demonstrate. We can do bool. Let's say we can call the function string new. So we want to allocate a new string. So what should we accept in any case? So let's actually do it like this. Let's do string pointer. We want to allocate and then return the string. Now here, if you are designing an API, like the question would be, what do you want to pass in as an argument to this function? Do you want to allocate a new string? Do you want to initialize it empty? Do you want to allocate it from a new string, like you pass in a new string and create it from there? You want to initialize it with some capacity? What should you put here? So I think that's a decision you can make. But for me, I tend to leave it like this, like you just do string new, and then here you pass in the initial capacity, like how big should your string be when you allocate it. So you can do size 2, capacity. Should we allow capacity of 0? No, we shouldn't allow capacity of 0, because on POSIX, if you call malloc and pass 0, it's actually undefined behavior, because on some implementations like on glibc, you will get actually a valid pointer here that you can free, but on other platforms it may not be what you want, because what is size 0? Yeah, so to avoid that, you normally have like you define like default capacity, and then you say we don't want strings less than 16 bytes, let's say. Okay, so it means that if the user passes in capacity that is less than 16, we basically use 16 as the default. So here you say that if capacity is less than, if capacity is 0, okay, then we override, we say capacity is equal to default capacity. We could as well use a ternary operator here, but it's okay. Then now we want to allocate the string on the heap, so we do string, this is s, is equal to malloc. Now we are calling malloc because we have to allocate that string on the heap, the whole struct. We want to allocate the whole struct, the members, so we need to know the size of that string. So that's where we are going to use size of string. So this one will give us 24 bytes because this is 8 bytes, this is 8 bytes, this is also 8 bytes. So if I point my mouse here, you see it gives us 24 bytes. Now we need to handle the case if this allocation fails. If there is no memory or there is fragmentation or something, and we get a null pointer. So here we say that if there is no s, or you say if s is equal to null. Okay, so I normally like doing if there is no s, because a null is false. In other words, it will evaluate to false. It means that something went wrong. You can either log a message, for example, you can do p error, malloc failed, or you give like string allocation failed, whichever message you want to put, and then you return null. So the caller has to check to make sure that they are actually getting a valid pointer. Okay, now an interesting thing is that malloc does not actually zero the memory. So these members, when you allocate them, this pointer is basically uninitialized. The size is some garbage value, the capacity is a garbage value, and data. So when you allocate, you have to initialize these objects, these members. So here we do s dot size is 0 since our string is empty. Then you do s dot capacity. So I think I skipped something. Before we even initialize, after allocating the whole string, now we need to actually allocate the data. Okay, because we allocated the struct, but we haven't yet allocated where to store the string. So this is where we do, now we do s dot data is equal to malloc. We are going to call malloc again because now we need to allocate the capacity. This is where we are going to store the string itself. And then we check the error again, which is if there is no s dot data. So if the malloc call failed, then we actually need to free the allocated struct, because if we don't, we leak memory. So let's free. We are freeing s, because remember, if malloc passes this check, it means that s actually has a valid pointer. So if we cannot allocate here, then we must free the above string to avoid leaking memory. And then we return null again. Okay. So if we can reach here, it means that we are successfully able to allocate enough capacity to store the string that the user actually wants to store here. So now we can safely say s dot capacity is equal to capacity, and then we can return s. So this is how you would allocate a new string, and you would use it like this. You would say string s is equal to string new. So I'm like, give me a new string which is like 16 with a capacity of 16. Allocate memory for a string large enough to store 16 bytes. Okay, now I have where to store my string, but that's not enough. I don't want to go into the details of how you would implement, how to, you know, like a full API for a string, but just to show you how you do it. Here you are going to, since we have our pointer for the struct and we know we can access the data, we can write directly to the string. So we can say strn copy. So we are copying into that string. So we do s.data. What are we copying to? Let's write the word hello world with a new line, with no new line. So how much are we copying? So this one takes the maximum number of characters of the source that it copies, no more than n characters of source to destination. So when you are putting the size, you must pass the size of the destination so that you don't cause a buffer overflow. We don't care about the size of this. We care about the destination, because it's the one, if you override, then you cause a buffer overflow. And obviously it's not the most robust implementation here, but I know that it is 16 bytes. So, and hello world is only 11 bytes with a null terminator, which makes them 12. So I can just say write not more than 12. It should still work. I could still pass 16 here or 15 and it would work. Okay, so obviously this one may fail, and in a robust implementation you may have to check for errors, truncation and all that, but that's not a topic for today. So I can print the string, just call it string, and then I do s.data. Now, this is not all. Remember, the moment you allocate memory with malloc or calloc or realloc, you have to free that memory. So what we normally do, you add another method here, void, you can do string free, then you also accept the pointer of the string which was allocated, and then here you can have a check that if someone passes a null pointer, then you have nothing to do. You just return, avoid double freeze, and then you free, basically you first free the data, you free s.data, then after freeing the data, you free the struct itself, like the main thing, you free s. Alright, so now since we are having this, it's a good practice to set the data to null, so that if someone tries to free it a second time, it's actually a valid operation, because freeing null is actually okay. I see some people, especially like YouTube, where people, if there is data then free it, it's actually redundant, because if it's null, free is actually a valid operation. Okay, and if there is a pointer, even if it's not valid, then the check will still be, will always return true, and free will obviously either fail or cause like a segmentation fault, but it will run. So I feel like sometimes the check is redundant. It makes us feel safe, but you know, even when I do it, but it's actually useless. Yeah. All right. And another thing that I see some people do, after freeing s, you set s to null. But I tell you, setting s to null here is useless, because the moment you pass s here, this is passed as a copy. So this pointer is actually passed, is copied. If you set this to null, the original value where s is pointing is not going to be affected. So passing, setting s to null here is actually very, is wrong. Yeah. All right. So here now you can call your function string free. Then you pass in s. All right. So basically, this is how we use it. And let me compile this and run where I can use this. I can actually compile it from here. So I call gcc call main.c and then run it. So we get string hello world, and our memory is free. So the takeaway from this malloc overview is that malloc will allocate as many bytes as you ask for. If it fails, it returns a null pointer and sets error no. Before I leave, maybe I should highlight how you can optimize this, because now you see we have two allocations, and every time you call malloc, it's going to allocate on the heap, and the heap will get fragmented eventually. So in performance critical code, you may want to avoid excessive dynamic allocation like this. Okay, so how can you make sure that this string is better and faster? I know I'm going a bit far, but this is not a beginner tutorial on string. This is actually a deep dive on allocations. So I have the liberty to go as far as I can. Now, one of the coolest things you can do in C is that there's something called a flexible array member, whereby now this one being the last member in the struct, I can actually allocate an unknown number of bytes by using this square bracket. Very interesting. This one is called a flexible array member. Flexible array member or FAM. It means that you see, if I point here, it changes from 24 bytes to 16 bytes because right now we don't know how big this thing is going to be. So it means that you can actually just copy this string over. Since we are not copying 24 bytes every time, you can allocate it. You can decide to allocate this string on the stack, and you just copy the data over. That's a decision you can make. But also, once we do it like this, it means that our string accesses, when you try to access the pointer to this data, for example here, string.data, the data is going to be in the same space as the size and capacity. So it's going to be like linearly allocated, which is very efficient for accesses in terms of cache or cache line. So how do we use the flexible array member? It means that when we allocate the struct, or when we allocate our string, we are going to allocate enough memory for the size of the string, and remember, size of the string excludes this. Then we add the capacity. So if we change the implementation, now it becomes that our string s is equal to malloc size of string plus capacity. Very interesting. We are allocating it as if the data just lives outside this struct in a contiguous space of memory. But it means that they are going to be in the same line, like so it will be contiguous, which is very efficient because now they live next to each other, and that can unlock a lot of performance benefits. So it means that you're allocating the struct itself plus the capacity. Now this capacity will represent where we are going to store the data. Okay, so for you, once you do it like that, now it means that you are having a single allocation. You don't need this. You don't need to allocate the data separately. But what you can do after allocating the whole string is that you can set s.data to null. Okay. Oh, this is actually you can't set it to null. You can't set it null because it's an array. You see, if you set it to null, this is not a pointer anymore. Okay. So as of now, this this memory is not yet initialized. So it's an array of unknown size, okay? But we can't set it to null. If we had passed in a string literal here, we could basically do a memo copy, okay? Copy the memory into this space. So how do we even initialize this? Okay. Now the best thing, in my opinion, is to use calloc. Okay. Now the difference is that calloc will zero the memory. So we are allocating the string plus the capacity. Okay. So what is the size of the string? It is 16 bytes. Now, if we wanted to zero the memory, we can start from 16 bytes going forward and basically call memset and zero the memory for the data. But I don't think we need to do that, because we can call calloc and it will just allocate the memory here over the string and the capacity for the data and zero it immediately, and we should be good to go. So you can change this to calloc failed. But now we have a single allocation, and even here we don't have to free the data because the data is allocated in the same space as the struct itself. Let's actually have like an alternative implementation which accepts the string itself. So we can say string from okay. So instead of reserving memory for a single, for basically reserving memory for a string we don't know, we can actually pass in a string, you know, and then copy it into the memory directly without having to go through all these hoops. So we need first to know how long is this string. So we do size t. It should be a null terminated string. So we call it size is equal to, we call the function strlen str. It should give us the length of the string. So how much memory do we need for this string? Obviously it should be size plus 1. So let's do size t required capacity is size plus 1. Plus 1 is for the null terminator, for the null byte. All right. So now we can allocate the string. So we can do string s. Can do string new. So what is the capacity? Of course, it's required capacity. Then we check here if s is null, means the allocation failed. So we return null. But if it's not, it means we have a valid string. So now we need to copy this new string into the allocated data. So if this is a whole string, we have the first 16 bytes, which contain then the data starts here. So the first 16 bytes contain the count, the first 8 bytes, and then the next 8 bytes. So this is size and capacity. After that, we have data. So it means we need to string copy, can do strlen copy or str copy, whatever, or you can use mem copy. Can actually do it like that. Mem copy. The destination is s dot data. So if you point to it, it shows you that it's at offset 16. Offset 16. So it's at 16 bytes from the start of this string. This is where we are copying. What is the source? Our source is str. And how much should we copy? We want to copy the size without the null terminator. But since we are sure we have enough memory here, we could as well just do like string copy, which is a dangerous function. But if you are really assured that you have memory there, then there's no, I think it's sometimes safe to use. Then you return S. Okay, so this one will copy the passed in string into the data divided by this string, and we should be good to go. I don't know whether I made any mistake. We are going to find out. So let me run this and then we see if we made any mistake. So here we can do string from, and then we call it hello world. Alright, so let's remove this and then we print the string. And it says hello world. Forget my weird terminal. So run main hello world. Can we check if there's any memory leak? So let's do var grind, run var grind. Alright, so 2 allocations, 2 frees, no leaks possible. So there's no memory leak. But this one says 2 allocations. I don't know where the second allocation is from, but we are basically doing only 1 allocation. Probably it's in the implementation of the glibc. Yeah, but so this is faster. It's a faster way of building strings with our malloc. So basically the new thing is that we use the flexible array member, and it has to be the last element in the struct to avoid another allocation. Instead of calling malloc for the struct and malloc for the data, we are basically only doing we are calling calloc. But actually I think there is a bug here, because we are not explicitly zeroing that data, okay? Which of course is wrong. There are many ways how we can do it, but I think we can still do memset here. We can call memset, then we pass in we do s.data, we are zeroing it, then we pass in the capacity, okay? Like the allocated capacity is what we are going to pass here. And then this, all the bytes starting from this offset are going to be filled with zeros. Yeah. So basically that is it. Let's compile and run again. Run main. It should still work. Alright. So basically, since I called this bit advanced, I think I've done my best to explain what malloc does, the conditions under which it fails. For example, what happens if you pass 0? There is an assurance that it should give you a valid pointer that you can free, but it's not cross-platform, and you may get undefined behavior. And for calloc, you pass the number of members you want to allocate. The guarantee is that it will zero the memory, but deep down it may actually not zero the memory immediately. So it's kind of tricky to know whether, but for you, you are guaranteed to know that, okay, the memory I'm going to get is going to be zeroed, and this is faster than calling malloc and then you call memset yourself. It's better to call calloc at once. And there may be a few other gotchas which I'm going to highlight. is that when you call calloc, it doesn't check for overflow, okay? Because this is the number of members and then the size. So the total memory is number of members times size. But what if the multiplication here overflows, you get integer overflow? What happens? You are going to get an error, okay? You may get it undefined behavior, really. And then you find that you are allocating an invalid block of memory, okay? So that's not what you may want. And another thing you may have to know is that on POSIX systems, you may not actually allocate too much memory. I think the maximum memory is indicated by pointer diff max. There is that constant. I think it's called PTR. Yeah, pointer diff max in standard int. If we import it, yeah, this is in standard int, and basically the maximum memory you can allocate using these functions, okay, on Linux. So the next function we're going to discuss is realloc. Realloc is a function you are going to use if you want to grow the memory. Let's say, like, we have our string implementation, and we want now to grow it. Maybe we are appending to the string and stuff like that. How do we go about growing this string? And these things are actually, this string implementation is very important in really knowing how you handle memory, because it has so many edge cases. For example, the way it is currently implemented, when we are trying to reallocate, there is there is something subtle here that you have to take care of. Let me show you what I mean. So let's call a function here. We call it bool string reserve. So we want to reserve capacity, or we can call it grow, or string ensure capacity, or reserve, whatever. So we pass in the string s and basically the new capacity. We call it capacity. We want to reserve enough capacity for what the user wants. Perhaps they want to grow the string and make it bigger. In IV implementation, since we are using a flexible array member, may just be like, because you cannot say s.data equals realloc. We cannot just reallocate. This we don't like. This is not a valid way of doing this. Okay, because this is an array. Basically, it's an array. We can't do that, and it's part of a struct. So how do you go about that? Okay, so this is whereby now in this case you have to reallocate the whole struct, unfortunately, because you can't free the data alone since it is part of the struct. So you would have to compute, let's say we call it required capacity, then you compute the size. Of course, I'm not doing the checks. Ideally here you should be like, if, for example, the capacity that the user wants is less than or equal to s dot capacity, it means the string is already large enough. So here we can return true. We have no work to do since the string is already large enough. Then you can check for 0 and all that, but I'm not going to do that. So for us here, we want to know, okay, how much capacity should we reallocate? It is what the user wants. And at this point, we know that it's bigger than what we have. But this is for the string, not for the whole struct. So the required memory will be, so here you actually call malloc again. So you do, you allocate a new string, then you call malloc, or you can call calloc, pass in 1, then you pass in size of string plus the capacity that the user wants. You repeat the same thing. So in other words, you can delegate and just call string new, avoid repetition, call it string new, pass in the capacity. If S, if not S, then you return false. Yeah. But now this string is not yet, we need to copy the data over. Okay, so this is new string. We need to copy data from the old string to the new string after expansion. So here we do mem, can we use str and copy. So we are copying into new string from the old string, so s.data. So how much data are we copying? We are copying the length of the string. Okay, we are copying how much is inside of this. Okay, and we are sure there is enough space for it because we just allocated it. So here we are copying s.size. S.size. And I think we have a problem here. We have a bug because we copied the string but we never updated the size of the string. So s.size is equal to size. Sorry, this is new string.data. Then you return true. So it means you've reserved enough memory for that. But again, this function feels redundant since we already have, string new and okay, string new basically allocates new memory and set size to 0, and here you would have another string. But it gets better when we actually go back our initial implementation of the string like this, where this is dynamically allocated, because I wanted to highlight how we use realloc. So let me go back to that. So here I'm going to call malloc with size of string. Then if that fails, we return 0. Then now we allocate the data, malloc, that is, we are allocating the capacity requested. Then we check, if not s.data, we free s and return null. Then we set the size to 0, we set the capacity with 0, the data, and then return s. Alright. Then during free, we need to free the data. S.data. Just for safety, you can also set the capacity to 0, but it doesn't change the s.capacity. And size to 0. Yeah. Since this is assumed to have been already allocated, and we are just trying to grow, you do string. You basically you need to allocate the new data only. So you do char, call it new data is equal to realloc. So realloc takes the original pointer which was allocated by either malloc, calloc, realloc, or similar function. So in this case it will be s dot data, because we are trying to allocate the string data, and then the size, the new size that we want to allocate. So this is capacity. So in other words, we are trying to grow the data pointer, like the memory that is allocated for that data. Here is the catch. If the allocation fails, it will return a null pointer. So commonly you will see people doing something like this. S.data is equal to S. So you reassign the same variable which you are trying to grow. Very, very common. But there is a potential memory leak. Should this fail for some reason, it will return a null pointer. And now you don't have access to the S.data anymore. So you can't even free it. So it's pointing to null. That's a potential memory leak. The second thing with realloc is what happens if this is null. Okay, if you call realloc with null, this is actually something common. You get your, for example here, you may decide that I want to implement a very simple string where initially this is null, and when someone tries to allocate, you basically call realloc on a null with null. Okay, so it means it will actually call malloc. If you, sorry, that's fine. All right, so you call realloc with null, it will call malloc, and then I'll basically return the pointer. So it's a very valid operation. Okay, so S.data. Let's go back to our implementation of new variable. So this is how you use it. You create a new variable, you check if new data is a valid pointer, or the other way around, you say if not, then you can say the error realloc failed, then you return null. So return false. The user can check and be like, oh, so it means we are not able to reserve the memory for this string. Otherwise, if it succeeds, this pointer is going to be freed by realloc, and you will have a new pointer. You are going to have a new pointer. The data is going to be copied over into the new pointer here, and then the pointer is going to be freed. So now all you are left with is to do S.data is equal to new data. And then, since we need to update the capacity of the string, we do S.capacity is equal to capacity. Basically, that's it. So let's demonstrate how to use this. Let's first let's use this example where we are actually allocating a string with a fixed number of bytes, 12 bytes. So once we allocate this, it should come here. We allocate 12 bytes because it is this is 12, but includes the null terminator, so its actual size is 11 bytes. So here we are allocating 11 plus 1, that's 12 bytes. We don't have any excess capacity, and then we want to grow this string. So let's call, let's say if not string reserve, then we pass in s. So we want to grow it how much? Maybe it's 24. bytes. Then we can record string free s, and we return what? -1 or 1. We exit the function. So if we reach here, it means we were able to reserve the memory. So the string should have a capacity to hold a string of 24 bytes. So we can actually copy the string. We can concatenate on that string. So how do you do that? You can call strncat string concat destination s.data plus. So where are we copying? We are starting from the end of this string. That's where we are starting from. The pointer. Here we are doing pointer arithmetic. We are basically moving to the end of the string. If we do s.data, we will basically overwrite the string. That's why we are doing plus. Of course, this is not the idiomatic way of doing it. Here you do strlen of s.data. What are we copying to? Hello world. Friends. Then n is basically the number of characters that we are copying from the source. It will copy not more than n. So here we have 10 characters, including the null terminator. So we can as well pass 10. I think that should work. Then we can try to delete it again. We'll call printf new string. If I messed up, then we won't find out this. Alright, so we get hello world, friends. So it works.